because today we'll focus on what is known as the mathematical tools of quantum mechanics. So, what are the mathematical tools you need in order to uh, get used to in using this beautiful quantum mechanics? Now, uh, so let me start by asking. Let me uh, uh, let me start by writing down a sentence, and then we'll start from there. That will. So let me write uh, that quantum mechanics quantum mechanics quantum mechanics is linear algebra. So how many of you agree? So what I'm saying that the mathematical structure of quantum mechanics is nothing but linear algebra. So how many of you understand this, or how many of you agree? When I'm saying that by linear algebra, I mean that the mathematical structure. So how many of you agree? Can you write down in the chat box? If you can write it down, that would be nice. So, do you agree? Are you there? Are you guys are there? Okay, I think some problem with.
Now, yeah, so do you agree with this statement? Why I'm calling quantum mechanics linear algebra? Can anyone tell me why I'm calling it linear algebra?
Because all the operators
Yes,
involved
why?
in quantum mechanics are linear operators only.
This is one reason. But we'll see why. So let me elaborate. So let me go back to your school days. And if you go back to your school days, so let me choose some other color. Say I take this, and I have a three-dimensional space. Okay, your x, your y, and your z or z. And in this three-dimensional space, uh, I can draw a vector like this. Say this vector I'm calling it v. Okay, it has a length, of course. So how do you express this vector v in this 3D space? In the 3D in three-dimensional space, a vector v can be expressed as follows. How do you do this? I have to take three components of this V along
X
three
plus plus
axis.
Y, isn't it?
Yes. So essentially what I need to do, I need to do say something like, say, I have a component like Vx. You want to call it Vx, it's fine. I think, yeah, let us call it Vx. And then I should multiply with Ex cap and then plus Vy, sorry, Ey cap plus, I think I should write it better. Vy easy. So what are these things? You know that these are this Ex, Ui and Ez. What are they? So they are unit vectors, isn't it? Okay. So in other words, and these are the components. These are the Vx, Vy, and Vz. These are three components. So Vx, Vy, Vz, they don't have any direction. The direction comes from here. Okay, the direction comes from here, from the unit vectors. So these are vectors of magnitude unity, magnitude 1. But since these are vectors, these vectors have direction. So Ex is along x-axis, Ez is along z-axis, and Ey is along y-axis. So in other words, these vectors actually, they form a basis. So do you agree with this statement that they form a basis for the vector, this V, in this three-dimensional space? So do you agree? Please write in the chat box. Please write in the chat box whether you are following. This is nothing very difficult, very simple thing. Very simple thing. Okay. Very good. And for example, you should know few things. Of course, in I can also write this as people have notations which are more familiar. People are familiar with. So this is something like Vx times I cap. You know this, plus Vy times j cap plus z times k cap. Same thing, only different notation. This I is not root over minus 1. This is unit vector along x-axis. Okay? Are you following? Excuse me. Please write in the chat box. Yeah. So this is just a different notation. Just a different notation. People are maybe, I think, more familiar with this notation. Just your notation, you choose your notation. So nothing else. Okay? As simple as that. Okay. Now, this is in 3D. Also, you know few things. For example, if I take a V and take a dot product of V with V, this is called dot product. And then what will be the answer? Can anyone tell me? Yes. So what I'm going to get something like Vx square plus Vy square plus Vz square. This is it. The dot product is a scalar, of course, it has no direction, and this is how the answer comes out: Vx square plus Vy square plus Vz square. Very simple, you know why? Because if I take dot product between I and I, what is the answer? Tell me. I dot I 1. Similarly, I dot j is 0. You know all these things. I'm not writing everything. Okay. Okay. So this is called V dot V, and this is called dot product. And there is also another name to this. This is called scalar product. You know this? This is called scalar product. And also from here you can calculate something like, if I this is essentially V square. So if I calculate this will be what? This will be Vx square plus Vi square. And what is this? Can anyone tell me what is this? You know what is this? There is a name to this. Yes, this is called norm of a vector. Norm or length. Just brushing up your memories. Just brushing up your memories in 3 dimension. Okay, fine so far. So I can move on. So let us make your life little more complicated. Say, consider not 3 dimension, consider a vector in n dimension. N dimension. Now I cannot represent this because I cannot draw n dimension here. Okay. So n means n could be anything. N equals to 3 is your 3 dimension. N equals to 2 is your 2 dimension. But n could be anything even greater than 3. It could be huge number. So you have in general you have a vector in n dimension. So n dimensional space what you have here. Now I can follow the same thing and I can write any vector in this n dimension. Say I call V. And let me write down this n, any vector V. I can, along each dimension, I can choose a unit vector. And then I take a linear combination of this unit vector, and that will give me any arbitrary vector in that n dimension. So essentially what I have here, okay, let me write down V1 like this. I cannot write Ex, Ey, Ez because I'll not have enough notation. So it is something like this. This is fine? Fine with you? Is it in any dimension? And what is there? You have this collection of this unit vector. And they form a basis. So I can take any arbitrary vector in that n-dimensional space and take a linear combination of these unit vectors and express that arbitrary vector. Is this clear? The statement is very simple. It should be clear. I did it for 3D and now I'm doing it for n dimension. Okay. Now I've been telling you that they are forming a basis, those forming a basis. What is so special about these vectors? Can anyone tell me? Other than their unit vector, anything special about E1, E2, E3? In 3D, it was Ex, Ey, and Ez. Maybe you can write it in the chat box. Yes, so somebody is linearly independent. So the point is, all these vectors shown here, they are linearly independent. Now what does it mean? Qualitative, it means that none of them can be expressed in terms of others. So I cannot take E1, I cannot express E1 in terms of E2, E3, anything else. For example, if I go to 3 dimension, I cannot express Ex in terms of Ey and Ez. This is qualitative statement. Is this clear? So if I choose a vector which is along x-axis, this vector cannot be expressed as by combining, say, 2 vectors along z and y-axis. Is this clear? So in other words, for example, if I take a linear combination like this, I take any coefficient C1, E1 plus C2, E2, Cn, En. This is 0 only when all C's are 0. This is important. Then only they are called linearly independent. So I can take these vectors, take linear combination all of them, and then the resultant is 0, and that is possible only when all the coefficients are 0. Okay, so this is what known as linearly independent vectors. So the point is as follows. So basically, what you do. Voice is not clear. Is it clear to others? The voice?
Yes, sir.
Yeah. So maybe some internet connection. Yeah. So the point is as follows, that any arbitrary vector you can express as a linear combination of n, and it is in dimension n independent, linearly independent vector. And you have already done this in quantum mechanics. Just go back to your particle in a box. Now, if you go to particle in a box problem, you remember that you had this one, psi 1, psi 2, psi n, isn't it? Each of them is normalized. Now, if it is normalized, what does it mean? Which basically means that psi I star, psi I, you remember this, no? Is 1. Which basically means, what is the length of the vector? Length or norm. This is equal to 1. Is this clear? Write down in the chat box. It was from 0 to L. Okay. So actually, this psi 1, psi 2, psi n are like E1, E2, E3. And any arbitrary wave function, psi, any arbitrary, anything, psi, any, within that box, I told you that you can write as a linear combination of Ci, psi I. Where I goes n. Is this clear? This is not very difficult. But see the analogy. See the analogy, okay? Now, this is one thing. Also, I had said that, okay, dx psi j star psi j, psi I, or psi I star, psi I, whatever. What was it?
0.
Delta ji. So, and it is equal to 0 if I is not equal to j, isn't it? What does it mean? It basically
Kronecker
means,
delta.
yes. So, Kronecker delta is fine, but what does it mean? It basically means that they are orthogonal.
Orthogonal to each other.
So, they are orthonormal as well as normalized. Now, what is orthonormal? Come back here. If I take E1 dot E7, what is the answer? What is the answer?
0.
0. So basically here also these basis vectors, they are normalized because they are unity. So the length is 1 and they are also orthonormal to each other. So they are also like wave function, they are like, you understand? So they are like, are you following? Just tell me. So they are like, they are linearly independent, they are normalized and they are orthonormal. So essentially what you have, the basis functions are linearly independent and orthonormal. And so basically this, they are orthogonal set. Just analogy. This is, so basically you can, what you are doing is essentially linear algebra in quantum mechanics. Because these wave functions are like vectors. But this is slightly different, you understand, because actually the statement is that so there is something called Hilbert space. Okay, this is an n-dimensional space. Space of complex vectors. And we have a special Hilbert space in quantum mechanics. This is called this is called L square. This is a space of square integrable functions. And what are these functions? These are nothing but wave functions. So you are following. So these are like wave functions or state functions. And these wave functions actually, they belong to n-dimensional space. Why I am saying complex vectors? Because in general this wave function could be complex. Because wave functions may be complex, no? There is no problem, no? Wave function could be complex. There is no such restriction. Yes. So complex means it has a real part and an imaginary part. So complex number essentially. But these are like vectors. So these are complex vectors, wave functions, and they belong to a space which is called Hilbert space, which I have written. You don't need to know more than that. But the condition is that these wave functions are square integrable functions. How many of you remember square integrability? So if I have two functions, so if I take f of x and g of x, so the square integrability means f star x into gx. I'm doing in one-dimensional coordinate space. This has to be what? What? Finite.
Some definite value, finite value.
Finite. So it cannot blow up. This integral cannot blow up. Is this clear? Okay? Is this clear? It is very important that these things get clear today. Is this clear? Yeah, very good. So now we are going to now change our notation little bit. We're going to change our rotations little bit, but before that, let me show you one thing. So there is something called, in quantum mechanics, there is something called free particle. How many of you know free particle in quantum mechanics? Yeah. So what is free particle? Can anyone tell me? What is free particle?
Sir, in particle in 1D box, we consider that it is that the particle is moving from in dimension 0 to L freely with the potential V is equals to 0.
No, you are not right. Particle inside a box is not a free particle. So free particle is a particle for which the force acting on the particle is
It is
zero.
not subject to any kind of force.
Yes, the force acting on the particle is zero. No force is acting on the particle. So the potential energy, this is not vector, huh? Is constant, or you can call it zero also, or zero. Because the force is minus in one dimension, it is the force. Clear? Okay, so minus dv dx equals to force. Now, but it is not between 0 and L, it is between minus infinity to plus infinity. As if you have a box, the length is infinity. It goes from minus infinity to plus infinity. Okay, and the particle is moving here. So what is the answer? Can anyone tell me the wave function for free particle? Actually, you will see the wave function for the free particle is given by this. This is one possibility. Exponential of ikx. Okay. If you do it very carefully, you will see that this is exponential of ikx. Okay. This is a wave function. Now, now let me try to normalize the wave function. What is this is the limit for free particle. What will be the answer? Tell me. This is going to be S star A, which I can take out. And psi star is going to be exponential of minus ikx into exponential of ikx into dx. What is the answer? What is the answer? Is you are integrating? Please tell me what is the answer. Goes to infinity. Blows up. The integral blows up. Are you convinced that the integral blows up? Because I have made it full screen, so I cannot see your chat. So maybe you can tell. Someone can tell.
Yes, sir.
So then what is then this function is not square integrable.
Yes, sir.
Okay, this function is not square integrable. Are you convinced? So basically this wave function and this wave function does not belong to this L square whatever Hilbert space. Sorry, convinced that does not belong to the Hilbert space. How many of you are convinced?
Yes, sir.
Yes, sir.
Okay. So how many of you are convinced? Okay, are convinced. Then what is the problem? Then the mathematician would say they don't belong to the Hilbert space, but then the physicists, they are more liberal, I would say. They will do okay. Yeah, they don't belong to the Hilbert space, but I can include them. So actually, what they have done, the physicists, they have taken these square integrable functions also these functions like exponential ikx, these are called plane waves. These are called plane waves. So they have taken these things also and they have included both of them, and they have enough space, and this is slightly different than the Hilbert space, and this is called rigged Hilbert space. And this plane wave, this exponential of ikx, you'll see in physics they use this a lot of time. This is in solid state physics they use. And they form a different type of normalization. There's something called delta function normalization, which we will not do. I think we did little bit in the last year, but not this year. Maybe we'll skip this. So that you should keep in mind. So okay, this exponential of ikx, they don't belong to Hilbert space, but we include this in the Hilbert space by just changing the Hilbert space to rigged Hilbert space. That you should remember. Is this clear? So this is only one exception, if exponential of ikx. Other than this function, all the other functions are actually square integrable in quantum mechanics. Okay. Now this is done. What I was doing, let me do one more thing. Let me go back and define this scalar product. Also known as inner product. How many of you know inner product, the term inner product? So I take two wave functions, psi1 and psi2, whatever you want to call it. Let us call it psi1 and psi2. Okay. And the definition is or psi a, psi b, whatever you want to call it. Say, let us call it psi a, psi b, psi j star psi I dx. Okay, this is your scalar product. Sorry, call me. This is your scalar product. This is the definition of scalar product, and I use a notation for this. This is a new notation for the scalar product. New way of writing. New means in this course we're introducing. So I take any two function. I can make it like this. For example, if I write phi comma psi, what will be the answer? Can anyone tell me? Maybe one of you can switch on your mic and tell me.
Integral phi star dot psi dx for one dimensional.
No, phi star dot psi dx.
Yeah.
I am doing it in x. Okay, I don't want to write deta again and again. Is this clear? Is this clear? Yeah, this thing has to be clear because this is very important. And this was not very difficult, I think. So far, what we have done is not very difficult. Okay. Okay, and now if I do one more thing, say like this, psi1, comma psi2, same thing. I'm writing again and again. So essentially, psi1 star, psi2 dx. Okay, you can also do it in d tau if you want. One more thing, if I do this, what will be the answer? Okay. I take a constant a and what is the answer? Can anyone tell me what should I write in the right hand side? What should I write in the right hand side? Tell me.
Complex conjugate of A integration psi1 star psi2 dx.
Yeah, so basically I should not write A, but I should write A star. And okay, I can take it outside. Essentially what I have is this. Since A is constant, I take it outside. This is fine? Is this fine?
Yes, sir.
So basically this is also another way of writing these things like this. Is this clear? Is it clear? So this is not very
Yes, sir.
difficult. Okay.
Yes.
Yeah. So now let me recall and revise something which we did in the last, not the last class. I think this is little while ago. This is called Hermitian operator. Okay. Now remember that if I assume say operator, I'm calling it Q cap. You can call it A, doesn't matter. Okay. Let us call it Q cap. So let me is a linear operator and is a Hermitian operator. Okay. Actually, you can go back and check your note. You will see that the definition was as follows. That I take this operator Q, operate on a function like psi2, multiplied from left by psi1 star, integrate over space, and this should be equal to, you remember this? Taking Q, operating on psi1, multiplying from left by psi2 star, integrating over space, and taking the complex conjugate of the whole thing. Can you check your notes and tell me whether I have done it correctly? Please check your notes and tell me that whether I have done this thing correctly.
So I have a question.
Yes.
So sometimes we take the dx or d tau term just after the integration, and sometimes we write it after. Means
Oh, does not really matter actually. You can write after.
is this before? Is this because there is the operator? That's why you are taking dx.
No. Dx you can also write this as dx. You can put the dx here. Doesn't matter. Does not matter. But tell me, just check your note. Maybe I use some other notation A cat for the operator. That you have to check and tell me. That
So we have used A operator.
yeah, you have used A operator. Okay. Now, if I write down this in my new notation, what would be the one? I write it like this: psi1, comma q psi2. I think we can write it like this. The left one. Okay. Is this clear? Is this clear? Tell me whether this is clear.
Yes, sir.
Yes, sir.
Now, now let me do one more thing. If I write down psi1 comma psi2 and take a complex conjugate of that. So look carefully, this psi q operating on psi2, this will give me another wave function, isn't it? It should give me another wave function. And I can call it psi2 prime. This is not taking derivative. I'm just putting prime, but it's not taking a derivative. Is it clear? That's psi1 comma q psi2. So now if I take this and take a complex conjugate of that, what will be the answer? Can anyone tell me? Just see the integral. Integral is going to be psi1 star psi2 dx complex conjugate. And what will be the answer? Tell me. This is going to be
psi1 psi2 star dx.
Psi2 star psi1.
Yeah, just write it like this. This is fine. This is fine. Just taking a complex conjugate the whole thing. And can I write it using this notation, this the first bracket notation? What will be the answer? What will be the answer?
Psi to psi1.
Yes. So this will be psi2 comma psi1. This is another property. This is another property, isn't it? Okay, this is fine. This is another property.
Yes, sir.
So now maybe I think we can do this way. If I take this quantity, what is there on your right hand side? If I take, I think that is better to do. So if I take this quantity, if I use my this notation, this first bracket notation, what is the answer of this quantity? This is nothing but psi2 comma q psi1 whole star. Are you convinced? All of you?
Yes, sir.
Yes, sir.
Fine. And then I can use this property. This one I can further write in a slightly different way. And if I use this property, what is going to be? This one, that psi1 comma psi2 whole star equal to
Q1
psi2 comma psi1.
psi2.
So basically you have q operating on psi1 comma psi2. Are you happy with this? Are you happy with this? Please tell me. I hope I have not done anything wrong here. I have not done any mistake here. Are you convinced? Just see. What is this? Because this, if you cannot follow, what is this? This q times psi1. I can call it something like psi1 tilde or psi1 prime. What I have here initially, it is nothing but psi2 comma psi1 prime star. And you know that this is equal to nothing but psi1 prime comma
Psi2.
psi2. This is exactly what I have done. Is it clear? It is not very difficult. If you write in the chat box, I cannot see. I have made it full screen. Earlier I was doing only 70%. Now I have done it full screen.
Yes, sir.
Yes, sir, it's clear.
Yeah,
Yes,
it
sir.
is not very difficult. Just
Sir,
do
it's clear.
yourself. Yeah. Okay. So basically then what I can do, I can rewrite my definition of Hermitian operator, and this is the one you'll find in the books. So what I'm going to get that your right hand side now has become Q psi 1 comma psi 2, which essentially means I put dx here, doesn't matter. Q psi 1 whole star into psi 2. Are you convinced? Just writing the thing in integral form. Are you convinced? And what I had here earlier, this is the expression. What I had here is and this is another definition, or maybe this is the better, not the better, I think this is more known way of writing the definition of Hermitian operator. This is also true. They are equivalent. Okay. If you read any book by Levine or any other book, you will see this is the way they have written, I guess. Just go and check. But you understand that what I have done here is the same. So this quantity here, this quantity, the size, this size 2 star Q psi 1 whole star is equal to this. Are you convinced? Please say. I cannot see the chat box.
Yes, sir.
Come up here.
Yes, sir.
Yeah. So this is the definition of Hermitian operator. So I am revisiting the definition. Okay. Now, now you are going to claim few things. That if I have this definition of this Hermitian operator, let me write down the definition again. I think it's not a bad idea to write it down. So what was that? So definition is, you should remember this, huh? Like you don't need to mug up, but you have to understand and remember. That's psi 1 star Q psi 2 must be equal to dx. Tell me. Q, what should be the Q? Psi 1 star psi 2. Okay, this is we're going to use. Now the claim, there are claims. The first claim is as follows. The claim 1 is that expectation value of Q in any psi, any arbitrary psi actually, is real. This is a statement. Okay. The statement is that the expectation value, the average value of the operator Q in psi of x is real. So what is that? What is this? So let me show. How do I calculate the expectation value of an operator Q? I assume this is normalized. It's normalized. This function is normalized. So how do I write down the expectation value? Remember, can anyone tell me what is the definition? I have only one psi, no? Because expectation value means, yeah, it is a diagonal term. So it is nothing but, let me write down dx. I am not psi star. It is a function of x, of course. Q. Psi. Are you fine? Are you fine with it?
Yes, yes, sir.
Yes, sir.
Yeah, very simple, very simple. And if I use our new notation, because if we are very lazy, how do I write? I can write like this. But again, this is equal to what? We'll see. We'll see. What is the, what is this equal to? Let me write down this now. Now what I do, I take Q and average value of Q and take a star. Now, if I want to show that the expectation value of Q is real, someone's mic is on. Please switch it off. When I ask a question, you can switch it on. Okay. So yeah. So if I take a complex conjugate of this guy Q average, expression of Q. So what is the answer? So I take a complex conjugate of this. Essentially, I'm taking a complex conjugate of this. What will be the answer? Tell me. See, this is nothing but psi star will become psi. Okay. And then Q times psi is some another psi. So basically, it will become times psi. Are you convinced with this?
Yes, sir.
Yes, sir.
Hmm?
Yes, sir. Just mention the complex conjugate sign, sir.
Yeah, this is complex conjugate. This is complex conjugate. The taking star means complex conjugate. Huh? I am taking complex conjugate of this quantity Q hat average. I am taking the complex conjugate of that. Okay. And then what you have here is this dx psi whatever. But this one I can rearrange actually. I just want to rearrange it and write it as doesn't matter because I can write it as Q psi just okay. Remember the trick is as follows. Whenever you have Q times psi, remember this Q times psi is actually some another new psi. It's something like psi prime. Okay. So then you can use this. This is something like psi prime, which is a new. It is not derivative, some other psi. Okay, this is like this. Okay, not a derivative, not derivative. You have to practice a little more in order to get used to. So what you have here is Q psi star psi. Okay. Now if Q is Hermitian, what happens? If Q is Hermitian, what happens? Hey, tell me. Someone tells me.
Equal.
The expectation value should be real.
No, don't tell me. External should be real. That we are going to prove. We have not proved
Both
it.
the expectation
We are
value of
going to
Q-
use this mathematical expression here shown. And if I use this quantity is going to be equal to what? Just
The
look at
frequency
it.
quantity. Yes.
Yes, it is Q psi 1 whole star psi 2. And this is going to be equal to then nothing but dx. You understand, no? You understand what I'm going to do? It is going to be
Yes,
psi
sir.
Yes,
star
sir.
Q hat psi. And what is this? Can anyone tell me what is this?
This
What
is
is
a
this?
psi
Psi
This is
Q
your
psi.
phi.
yes. Because this is nothing but psi comma Q psi, isn't it? And this is nothing but what? Nothing but your expectation value of Q. What I have proved doing this, that Q, expectation value of Q star is equal to Q. What does it mean? This is possible when? This means what? This
When
means we
Q
have
is
proved
real.
When it
that
is
the
real.
expectation value of the operator, Hermitian operator Q is real. This is claim 1. And what is claim 2? So the claim 2 I'm going to write, and then you like it because you have been hearing the claim 2 in all the other courses in quantum mechanics. But I don't think if you are not from physics, it is done properly. Claim 2 is now the eigenvalues of Q are real. This is you have been hearing, isn't it? Because Q is Hermitian, remember, Hermitian. So the eigenvalue of one Hermitian of a Hermitian operator is real. And in many times it is the way it is taught that okay, what is an Hermitian operator? The eigenvalue is real. This is not correct. This is a consequence. And we will prove that now. Are you following? Somebody says yes, please.
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
So,
sir.
but I warn you, it is not the definition of Hermitian operator. If somebody tells you this is not correct, definition is the one I discussed so far. The consequence is this. Now, this is not very easy to show. For example, I can take Q and operate on say something like psi1, and I say the eigenvalue is Q1 times psi1. This is eigenvalue equation. Okay. So, and now in that state psi1, if I calculate the excitation value of Q in that state psi1, remember that state psi1, and this is going to be nothing but, I just write down again. You have to practice little bit, okay? And you understand I am using the eigenvalue equation. I can put Q1 outside. Now I have already shown that the expectation value is real, isn't it? Even the more general one I have shown already. Claim 1, let's look at claim 1. Claim 1 is the expectation value of Q is real. So this is real. Are you convinced this is real?
Yes, sir.
Proved, already proved. Claim 1. We have proved it for any arbitrary state psi. This is for psi 1. It should also be true. And what is this quantity? Now this dx I star, this part is real. Has to be, no? This I star psi, no? Kind of thing. It has to be real. We just, and the whole thing is real. Oh, then what is the answer? This is real. Whole thing is also real. Why? Because Q psi 1 has to be equal to Q psi 1 in this is fine. The only possibility is what? What is the answer? That Q1,
Q1
the
is also
eigenvalue is here. So now you are convinced, you are happy, and now you should be happy actually. These you have been hearing since I don't know ages. Let me ask Dibojit and others from BS. It was done in physics maybe, no? PH 107. I'm not sure.
In our time, this vector algebra was not taught, but last year, since I was TA for this course, it was taught. This commutators and all these things were discussed.
Yeah. But now please tell others and tell each other, Hermitian operator is not an operator whose eigenvalue is real. Hermitian operator has a mathematical definition, and a consequence of that is that the eigenvalues of a Hermitian operator
Yes, sir.
are real. Okay? This is very important, huh? This you have learned. So claim 1, claim 2. So let us see if I can claim, if I have few more claims. Yes, we have few more claims. This is like Claim 3. What is the time? I'm not keeping track. What is the time? I'm not going to stop.
12:05.
12:05, sir.
Yes. Yeah. So claim 3. Now the claim 3 is which I have done. Eigenvalues can be organized to satisfy. What is the satisfaction? Satisfy this, that dx psi I star psi j equals to delta I. And what is this called? This is called orthonormality. We have discussed it, no? But we have said that, okay, that if you have a Hermitian operator like particular box Hamiltonian, then the eigenfunctions will form an orthonormal set. That is what I said, isn't it? But we had not, what is that called? Proved it. Okay? Okay, so let us assume that, sorry for this. Today's class is very important because this is not taught in quantum chemistry, but it should be taught. Let us assume that, okay, your Qi is not equal to Qj. So none of the eigenvalues are same. This is the assumption. Okay. Now, if Q is Hermitian, this capital is Hermitian. If Q is Hermitian, what is the definition? You remember that. Let me write down this. Ij I am doing now. Psi I star Q psi j whatever dx, that must be equal to I'm writing it again. This is fine. Dx you can put it here. Fine.
Sir.
If you don't like it, put the dx here. So the definition of Hermitian operator. Okay. Now, if I expand this, the left hand side, what I'm going to get? I'm going to get, this is nothing but Qj dx psi star psi j. But remember, I cannot put this equal to 0. Why? Because I'm going to prove that it is equal to 0 if I is not equal to j. You understand?
Yes, sir.
Psi I star psi j integral when I is not equal to j is 0. You know, but for the timing thing you don't know because you're going to prove that. Okay. So this is what you get from your left hand side, and from right hand side, what should you get? Tell me what you are going to get from right hand side.
Q1 star integration dx
Yes.
psi 1.
So let me expand this. When Q operating on psi 1 will give you like psi I will give you Qi. So this Qi will come out. Okay, Qi will come out, but then it is inside star, so it has to be Qi star. Are you following me? This is Qi star, and then what you have here is psi I star psi j. Is this clear?
Yes, sir.
Yes, sir.
Now this is, I'm calling it equation 1. I'm calling it equation 2. Okay. Do 1 minus 2. something like that. What I'm going to get? I'm going to get something like if I do something like this, what I'm going to get is like yeah, 1 minus 2 or 2 minus 1 doesn't matter. So if I do 1 minus 2, it will give me qj minus qi star into integral dx. But eigenvalues are real for Hermitian operator. So what is qi star?
QI.
It's just qi. So this integral is nothing but qj minus qi into integral dx psi I star psi j. We had assumed what?
The QJ not equals to QI.
Qj is not equals to Qy.
This we had assumed. Okay. So this is not equal to 0. Fine. Not equal to 0. But the left hand side should be equal to right hand side, na? Because we are using this Hermitian operator property, isn't it? But this the whole thing should be 0, isn't it? Because 1 is equal to, oh sorry, because 1 is equal to 0 because of Hermitian property. Because sometimes I have problem with the pen. Because 1 is equal to 2, Q is Hermitian. Okay. So what is the answer then? Someone tells me from MSc Maths. The whole quantity is 0. But
Then
this quantity cannot be 0. Then how it is possible it is 0?
Then integration of
When
dx
integral is
The
0.
integration part not visible.
This has to be 0. Okay. And this is essentially we have formed. So essentially, in other words, again, these things are not taught in chemistry course, but it should be taught. I don't think the math here is very difficult. Don't get scared. Nothing to scared. Practice little bit, you can do it. Okay. But very important that you understand all these things. This is claim 3. So we'll have one more claim and then we'll take questions. But one small thing here, I should say that what happens when Qi equals to Qj? Can you have a situation? Can you have a situation that Qi equals to Qj?
Possible when I equals to j.
No, we didn't have a situation when. Yes, possible. Why? This is called degeneracy. We have not discussed. We'll discuss in the next class. There's something called particle in 3D box. Where you can see there's something of degeneracy, or even in hydrogen atom, isn't it? If I fix the quantum number n, the energy is the same, isn't it? For n equal to 2. 2s and 2p will have the same energy eigenvalue, okay? Then this proof will not work. But again, see the statement, it says that it can be organized. I am not saying the eigenvalues satisfy. I said it can be organized to satisfy. I can always do something so that it is arranged in such a way that it is satisfying this. So if you have degeneracy, you will see later that you can take linear combination of these degenerate states and form states which are orthogonal, of course. Degenerate states are also orthogonal, but this proof will not go. Okay, we'll just, this is one thing, a short note, small note on this. So let us do the fourth claim and the last claim here. And the last claim is, let me write it down because I don't write it down. Sorry. Claim 4, and the claim 4 says, okay, that that you have already know. Actually, the statement is as follows: the eigenfunctions of Q, which I have already said, form a set of basic function okay, any reasonable psi any function can be written as superposition of superposition means linear combination. This is what I want, the linear combination. Q eigenfunctions of Q. This I have told you, no, the statement. The statement I had given. So this is another way of, I'm just stating it again. This is the claim 4, and essentially any arbitrary function I take, psi of x, and I can take it as a, I want to call it something like Ci function of x. Okay, so this is nothing but, you understand this, no? This is not a very difficult thing. The statement itself. Any arbitrary function. I told you in particular box, within that interval 0 and L, the way you constructed the particular box, any function can be expressed as a linear combination of the eigenfunctions. This is essentially the same thing I am doing. So let us calculate this. Psi comma psi. How do I calculate psi comma psi? Psi comma psi is
Integration dx psi star psi.
Yes, psi star psi. And I know that the expression of psi, okay, and I can do this. I'm not going to do it, but let us do one more thing. This I have done it actually. You can do it. Essentially, what I have here is this: Ci psi I star into, I can use a different dummy variable here, and then what is the answer? Because they are orthonormal set, the answer is, remember that only the diagonal terms will survive. Is it? Are you following? Only diagonal terms will survive. So essentially what I have here is Ci star Ci. This is the answer. Because this will give me something like this: Ci star Cj and then delta Ij. Okay, I comma j, and this will give me this. Essentially what I have here is sum over I Ci. Sorry, it's on sometimes. Now, what about this? Taking, if I take a scalar product like this, psi1 comma psi. What is the answer? The integral is dx psi1 star psi. And this is going to be what? Tell me. This is psi1 star. Psi is what? Somebody can tell me actually. Ci, psi I. This is fine? You can switch on the mic. One of you can switch on the mic and tell me whether I am doing it correct.
Yes, sir. Fine, sir.
Yeah. So, and what is the answer? What is the answer?
C1 star Ci.
Yes. So what I'm going to get something like I is there, Ci is there, dx is there. But then you have psi1 star psi j. Now remember that actually yeah, the whole thing is this is something like I, Ci, and the integral is, you understand, the integral is dx psi1 star psi I. This is not j, this is I, I. Psi I. Okay. So, and what is this? You know that when I equals to 1, then only it will be now when I equals to 1, then only it will
Fine.
isn't it? This will be varied, isn't it? Now let us, if I so this is, and the answer is going to be something like alpha 1 actually, not alpha 1, C1 rather. C1. So just check carefully that it's C1. But I can do the another thing. I can do, this was psi 1. If I do for psi I comma psi, what is the answer? This is something like psi I star psi, and this is going to be psi I star, and the psi I can write it as a linear combination of, now I use a different, because I should not be using I here, I should use j, another index, the dummy variable rather, because if I use I, then I'll have confusion here. I should use different I and j. And what is the answer to this? Essentially you have something like j, but then you have an integral in general, psi I star psi j. And what is the answer? Can anyone tell me?
Ci.
Cj, and this one you know, delta ij, isn't it? Delta ij. But only one term will survive, isn't it? When I equals to j. Only one term survives. Just wait for a minute, yeah. So this will give me only one term survives. And this one term is nothing but Ci. Are you convinced this is Ci? Are you convinced this is Ci?
Yes, sir.
Yes, sir.
Yes, sir.
And the one I did here, psi comma psi, what is the answer? If psi is normalized, this has to be 1. So this is the way to calculate the coefficient. I take psi I comma psi, that gives you the coefficient Ci. And one more thing we'll do, just state, I'm not going to do it in detail because this is the scope of this course, beyond the scope of this course, but we'll do, just write it down. This is called measurement postulate. I have to copy the language because the language is very important here. It says that if we measure Q in the state psi, the possible values obtained are the eigenfunction, of course, Q1, Q2, like this. And the probability I'm calling it Pi to measure Qi is Pi mod of, which is nothing but and it says that after the outcome, say Qi, the state of the system becomes psi of x equal to psi of I x, and this is called nothing but a name to this. Anyone knows what is it called? It's called collapse of the wave function. So now, any question on this measurement postulate? We'll take it from there. I think you can read it right there. So yes. So the measurement postulate said that if you measure the quantity associated with the Hermitian operator, so it could be a momentum, could be your total energy, whatever. If you measure the state psi, the possible values obtained are the eigenfunctions, not the eigenfunction, eigenvalues, Q1, Q2, whatever. And the probability is essentially the coefficient square, isn't it? Q1 is for psi1, so the coefficient with which you mix psi1. Because you remember that your don't forget that your psi is, what is important here is your psi, the wave function is your C1, psi1 plus C2 psi10. So this coefficient will tell you how much psi1 you are mixing, how much psi2 you are mixing, how much psi3 you are mixing. So the coefficient square would give you the probability of to measure Q1. Okay, Qi rather, Pi for Qi. So C1 square, mod of C1 square is for Q1, mod of C2 square is for Q2, so on and so forth. And after the outcome, after you measure, the state of the system actually collapses to that particular eigenstate. And this is called the collapse of the wave function. So each time I measure, say I try to measure the particle box energy, first time I get energy say E2. So essentially my after measurement, my system collapses to psi2. Next time I measure it, it collapses to say phi5. So my wave function collapses to psi5, something like that. But the probability of getting psi1, psi2, psi3, psi3, psi4, that depends on the state in which the psi1, psi2, psi3 are there, in what proportion they are mixed in that state. Okay. So the coefficient square will tell you what is the probability. Higher the coefficient square, higher is the probability. So I can take, for example, I can take linear combination of say psi1 and psi2, and I make C1 and C2 both equal. Both are equal. Okay. I can make it both are equal. So that C1 square plus C2 square equal to 1, but C1 equal to C2. So basically C1 square is half. Okay, C1 square is half. So C1 is 1 over root 2, C2 is 1 over root 2. In that case, it is equally probable that I get, if I make many measurements, half of the time I will get psi1, half of the time I will get psi2. But if I do other way, for example, if I take the value of C1 is such that C1 is 75% and C2 is 25%. C1 square is 0.75 and C2 square is 0.25. Then if I do many measurements, then 75% time I'll get psi1 and 25% time I'll get psi2. Is this clear? I think that is enough for this course. You don't need to go deeper than this. Okay? I
Yes,
don't
sir.
think we need to go deeper than this. And with this, we'll conclude today. But the next day, we'll do little more, and then we'll briefly mention few things in particle in 3D box. And I think I plan to go and start doing hydrogen atom problem, which is very important for your chemistry course. Is this clear? Okay, so with that, I'm going to stop presenting, and also I'm going to stop recording. Thank you very much.